Welcome back to Bytes of Pi. Today's video we're going to cover the first part of recursion, specifically recursion within Java. Recursion refers to the programming practice of having a method call itself. Within a language, recursion could be compared to a bad practice called circular definition. So if you think about it, let's take an example of punctuality. I could say that punctuality really is the characteristic of being punctual. Now, in English or any other language, this is kind of discouraged because it assumes that the person knows what the term means. It's a bad practice if you to try and explain to somebody what something is by saying it is the characteristic of being itself. So this is a bad practice in English, but it's really good when it comes to mathematics or even programming, and we'll get into that. Let's consider a list of integers. You could say 87, 24, 31, or 2. You can define a list as either a number or a number, comma, another list. So in this example, I'm using the concept of a list to define itself. All lists follow this kind of pattern. It's either a number by itself or a number, a comma, followed by another list. So let's take this example and take our definition. Remember, number or a number, comma, a list. Well, the first definition is it is a number, 87, comma, another list. And let's take a look at the definition of that list. Well, that list is a number, 24, comma, another list, which is this part. Now let's take a look at that part. That list is really a number, 31, comma, another list. And finally, let's take a look at this list. It's a number. So if you remember our definition, a list is either a number, comma, another list, or it's a number by itself. Here you can see how that works out, and it works really well and elegantly in math and computer science. Infinite recursion. At this point, we've already talked about loops, and we've seen what an infinite loop can do. An infinite recursion is very simple. It is very similar to an infinite loop. All recursive definitions must have a non-recursive part, a place where it kind of stops and starts returning back values. Same thing with like a loop. If you never reach that end case, you're always going to continue on. It could be infinitely. A definition without a non-recursive part causes an infinite recursion. The non-recursive part, or point where the recursion stops, is usually known as the base case. So where I'm able to return something without having to call myself again, directly or indirectly, that's what I call my base case. It's usually a good practice whenever you're creating a recursive function to consider your base case first. As long as you have your base case, you can kind of craft the rest of your recursion around it. Now you can have more than one base case, and you can have more than one recursive step, but we'll get into that in more advanced designs. Let's take a look at recursion within math. You've probably already been exposed to recursion in some form or fashion within math. Let's take the definition of a factorial. N factorial. For any positive integer n, remember positive integer, is defined to be the product, which is multiplication, between 1 and all and n inclusive. So essentially n is a variable where I can plug in any positive number and use this algorithm to get the value. So first let's start again with our base case. Our base case is 1 factorial. If I did 1 minus 1, it'd be 0, and it would no longer be a positive integer. So our base case, the very last case, is 1 factorial. We'll keep this in mind as we go through this. So n factorial, any number, is really n times n minus 1 factorial. And let's take a look at that. Let's try and solve 5 factorial recursively. How a computer would look at it. We'll take the problem 5 factorial equals something. Well, what is that something? It's n times n minus 1 factorial. Well, what is that? It's 5 times 4 factorial. Well, let's take a look. Before we solve anything, let's take a look at 4 factorial. Well, 4 factorial is really 4 times 3 factorial. Okay, there's still an unknown part of it here, the 3 factorial, so before we do any solving, we're going to go into the 3 factorial. What is 3 factorial? 3 factorial is really 3 times 2 factorial. Again, we still have an unknown part of it, so we go into the 2 factorial. What is 2 factorial? 2 factorial is really 2 times 1 factorial. And here's where we hit our base case. So we know that we no longer have to keep looking at ourselves to figure out what factorial is. We know that 1 factorial is really 1. So we'll multiply 1 times 2 and we'll get 2. So now we no longer have this unknown. 2 factorial is now we know is 2. So we'll plug that back in. We'll recursively come back to the function that called us, plugging in 2. So we know that 3 factorial is really 3 times 2. So we'll figure out that 3 times 2 is 6, and now we've recovered another unknown. This 3 factorial is now we know is 6. Okay, so we'll use that in our next stepping back through the equation. 4 times 6 is 24. So now we've recovered this unknown. 4 factorial is really 24. Now we have 5 times 24. We now finally figured out our last unknown. 5 factorial is really 120. That's how you would solve. That's essentially how you would solve it. You really wouldn't solve anything until you got to your base case. Once you get to your base case, suddenly the unknowns start to become knowns, and they plug themselves back in. A recursive method is a method that can call itself. This method needs to be able to handle one or more base cases. This is where the recursion ends and starts returning back, and one or more recursive cases where the function calls itself. Note, each time the method calls itself, it keeps its own set of local variables and parameters. So if I had a function foo, and I had a variable x equals 5, and I get down here to this other case where I change x here, say x equals x minus 2, and I call myself again. When I come back into foo the second time, x is now 5 again, because it keeps its own copy of x. The previous version of foo has its own copy of x that got decremented by 2, so it's 3. It's 3 back here in the previous version of foo. But as I come into the new function, I have a new copy of x, which is now set back to 5. So this is something to keep in mind. We're going to go through a demo later on, and I'll kind of show this to you. We'll take a simpler case called summation. You may have seen summation notation where we use sigma. It's essentially the addition of a sequence of numbers. Think factorial, but using addition rather than multiplication. It may look kind of complex, the notation, but really it's fairly simple. Instead of 3 times 2 times 1, it's really 3 plus 2 plus 1. So here's sigma. Essentially, we plug in, we still have the variable n, and as n goes to 1, we add up we add those numbers up. So really n sigma to I equals 1 is really n plus n minus 1 sigma I equals 1, which is really n plus n minus 1 plus n minus 2 sigma I over 1. That looks fairly complex because we got this Greek lettering in here, but let's plug in the number 3. So really 3 sigma is really 3 plus 2 sigma, which is really 3 plus 2 plus 1 sigma, and we've reached our base case here because I is equal to 1. 3 plus 2 plus 1, which is really 6. So at this point, we're going to hop over to actual code and walk through a recursive function. So here I have a summation function. Here I have my base case. I'm going to keep adding until number reaches 1. And here's my recursive section. I'm going to return I'm going to return summation of number minus 1, so I'm going to keep subtracting. So in the first time through it'll be 4, so it'll be 5 plus whatever the summation of 4 is. I'll return that back as a result and then return that result as the final. So let's trace through it and watch what happens. Now I have watch variables. You may not be able to see it up here as we trace through it, but I am putting a watch statement on these two variables, result and num. So we go through it. We're going to start right here at the top, and we're going to step into the function. So here we are, num equals 5. We haven't set the value yet. Num equals 5, and we're going to step through this. Num is not equal 1, so we're going to return 5 plus the summation of num minus 1, or 4. So let's step into that. Here we are again, num. Now this is our second time through summation, so we've just called ourselves recursively. Notice num is now 4 because we're passing in 4. Result still hasn't changed. It's keeping its own result. And we'll step into this. Num is still not equal to 1, so we're going to call num plus 4 plus the summation of 3. So let's step into that. Num is now 3. Num is still not 1, so we're going to step over into that, and we're going to step into that. Num is 2. So we've already called ourselves recursively multiple times. You can actually see it here in the thread class where we are in our recursion here. You see we've called summation 4 times. Let's keep going. Alright, we're still not equal to 1 yet, so we're going to step into this. Now we're equal to 1. So now we're in our base case. And we're not going to call ourselves again. We're going to return 1 back. So let's return 1 and see what happens. Okay, we return. Now we're back into our other case where num is equal to 2 and the summation of 2 is 1. We're going to set, if you take a look at result is now 3. Okay, we're going to return that. So 3 is being returned back to where num is 3, so 3 plus 3 will equal 6. So result is now 6. Watch the values go up. So we're at the 3 point in recursion. Let's keep going. We're at the 4 point in recursion, where the summation of 3 is 10. I'm sorry, summation of 3 plus, so we have 6 plus 4 is 10. We're returning that value. Now we're at the original case where it's 5. Result is now 15. We return 15 and print it out. Oh, print it out. And there we have it, 15. That concludes our presentation. Thanks for watching.